Hey everyone, it's your tutor Lucas here, and today we're talking exponent rules. Our first rule is the product rule, and in textbooks all these rules come with formulas with a bunch of variables in them, but the key you're looking for is that base, the a, is the same, where the exponents could be anything. So in short, if we're multiplying two exponents with the same base, then we can just add the exponents together. For example, if we had 3 to the 5 times 3 to the 6, they both have a base of 3, and that base won't change, so your answer will still have a base of 3. However, now we're going to add the 5 and the 6 to get 3 to the 11. And the reason why we add these exponents is because we can break each of these 3's into their pieces. For instance, 3 to the 5 would be 3 times 3, 5 times, where 3 to the 6 would be 3 times 3, 6 times. And if we multiply all those together, we're going to end up with 11 3's, which is what it simplifies to. Here's a similar example, but with a variable as the base. Remember, as long as your bases are the same, your answer's base will stay the same, so we still get x. And the product rule says if I'm multiplying my bases, I'm going to add the exponents. So 2 plus 4 would give us x to the 6. Next comes the quotient rule. Remember, quotient also means divide. The quotient rule says if we have two bases that are the same and they're dividing, then we take those two exponents and we subtract them. So for this example, remember, for the product and quotient rule, if the bases are the same, they're going to stay the same. Only the exponents change, and the quotient rule says we subtract them. So 3 minus 2 is 1. So technically this is correct, but anything raised to the 1 is just itself, so we can just write 5 in this case. And just like the product rule, if we think of these expanded out, 5 to the 3 would be 3 5's, 5 to the 2 would be 2 5's, and every 1 5 on top can cancel out with 1 on bottom, and so we would be left with a 1 5 up top. And again, an example with variables, as long as both your variables are the same, it's going to stay the same variable. We're just going to subtract the exponents. So 6 minus 3 would give us y to the 3. And next we've got the power of a power. Remember, the word power in math just means exponent. So this is basically saying exponent on top of an exponent. And so this is saying if you have a term that has an exponent and another exponent outside of that, then you can multiply those exponents together. But again, keep the base the same. So for this example, we would have 5 squared, then raise that to the 4, which means we would want to multiply the 2 and the 4 together, but keep the base the same. And 2 times 4 would give us 5 to the 8. Another way to think of this rule is saying that we have 4 groups of 5 squared. And if you look at it this way, it just becomes another version of the product rule, where all of our bases are 5, and so we would just add the exponents. Multiplying these together is just a shortcut. Another example using a variable, x raised to the 5 raised to the 5 again, means we would multiply our 5's together, but keep our base the same. 5 times 5 would give us x to the 25. And then comes our power of a product rule, exponent with multiplying. And so this is a case where we have two things that are different multiplying together with the same exponent on top. And you can think of that exponent like it distributes in to where each of the bases get the same exponent. So here we have an example with a number and a variable, both raised to the 4. And that 4 is going to distribute to both the 3 and the c and become 3 to the 4 times c to the 4. Even if they have more than two things in those parentheses, as long as they're all multiplying and the exponent is outside of everything, then it's going to distribute into each individual piece. And again, all your bases will stay the same. They're just each going to gain the exponent. Our last one for this video will be the power of a quotient, exponent on top of division. And so similar to the last rule, if you have two different things that are dividing, an exponent on top of the whole thing, that exponent will go to everything on the top and the bottom of that fraction. Again, our bases don't change. They just each gain the exponent. So for instance, if we had like 4 over 5 raised to the second power, that 2 will go on top of both the 4 and the 5, like so. Another example with some variables. As long as that exponent is outside of all the parentheses, the 4 is going to go to each individual piece, just like this. Now I can understand looking at this can look like a lot, but just try to remember the key details. If your bases are the same and you're multiplying, add the exponents. If your bases are the same and you're dividing, subtract the exponents. If you're stacking exponents on top of each other, those exponents will multiply, but the base will stay the same. And whether you're multiplying or dividing, if there's an exponent outside of the parentheses, it's going to distribute to everything inside, and every piece within the parentheses will get that exponent. And a way that they could take all these rules and make them harder is by combining a couple of them together. Here are 4 examples that have some combos of the rules. Try to only look at one at a time and not get intimidated by what's going on. We're going to break it down piece by piece, and I promise it's not as bad as it looks. So looking at our first example here, I personally like to start with the top of the fraction and then work my way down, and I see stacked exponents, which means we need to multiply. And whenever there's a fraction, I find it helpful to start with the fraction bar, because anything we simplify on the top, we'll just leave on the top for now. Remember, your base stays the same, and we multiply the exponents. 2 times 4 gives us 3 to the 8, and so far we didn't do anything to the bottom, so we can just bring that straight over. And now it looks less complicated because we have a fraction with our bases the same, which means we just subtract the exponents. Our base will stay the same, and 8 minus 3 gives us 3 to the 5. Looking at the green example next, again, since we're starting with a fraction, I start with the fraction bar, and focusing on the top, we have an exponent on the outside, and just like the previous problem, as we distribute this 2, we're going to multiply by the exponents that are already there. X to the 2 times 2 is x to the 4, and y to the 3 times 2 is y to the 6. We didn't do anything with this y yet, so we can bring it over. Now here's our new setup. Always with your quotient rule, the bases have to be the same. So since this x to the 4 has no other x's around, it's going to stay the same. Anytime you have a number or a variable that doesn't have an exponent, there's always an invisible 1. So now we can use the quotient rule because we have 6 y's on top and 1 on bottom. So our new answer for y's would be 6 minus 1, which is 5. A question you may be asking yourself, should my y to the 5 go on the top of the fraction or should it go on the bottom of the fraction? There are a few ways to think of this, but ultimately wherever you started with the most y's, in this case 6 is bigger than 1, your answer will always go wherever there were more to start. And in this case we have nothing left on the bottom, but remember there's always an invisible 1 multiplying by our variables, so that invisible 1 would be left behind, and anything divided by 1 is itself, so we can just leave our answer like this. Next up is purple. These types of problems show up a lot on exams, and it can sometimes be overwhelming when you first look at them. But remember, all our rules follow the same bases, so we can split this up into A's, B's, and C's separately, where first we're just going to look at what happens with our A's. Again, we have a fraction for this one, so we're talking quotient rule, and we've got 2 A's on the top and an invisible 1 A on the bottom, so 2 minus 1 would give us 1 A up top because there were more A's up top to start. Now, if we just look at the b's, we have 4 on top and 2 on bottom, so we would subtract 4 minus 2 to get 2 b's up top because there were more b's up top to start. And now for our c's, there's an invisible 1 here, so technically we would do 1 minus 3. However, that gives us a negative number as an exponent, which can be confusing for some people. So a trick for this one, if I were to switch that subtraction around, I would end up with a positive 2, and because there were more c's on bottom, my answer ends up on bottom. Another video all about negative exponents will be coming soon, so if you're curious about those, stay tuned. But ultimately, this is our answer for this one. However, anytime you have an exponent of 1, we don't have to write it, so this would be considered more correct. And last but not least, we've got orange. Quite a few things going on with this one. We see a fraction with e's on top and on bottom, and separately we've got d's only on top, but one that's in parentheses with a stacked exponent, while another is just multiplying off to the side. Ultimately, there are a few different ways you can approach this one. I'm going to ignore the d's for right now and just focus on the e's. Since we've been doing quotient rule quite a bit, we're going to repeat that same process where we have 5 e's on the bottom and 2 e's on the top. Since there are more e's on the bottom, my answer for e will end up on the bottom. We could subtract them in the normal way to end up with 3 extra e's. Again, if this is kind of confusing to see in your head, it may be helpful to expand them at the beginning, because here we have 2 e's on the top of the fraction and 5 e's on the bottom. Every 1 e on the top will cancel with 1 e on the bottom, and we're left with 3 e's on the bottom of the fraction. So now that we've done our e's, we can focus on the d's. This d is just hanging out by the end, so we'll wait to do that one later. Let's focus on the stacked exponents. And again, with stacked exponents, we multiply. So 3 times 4 would simplify this piece into d to the 12. And again, we haven't touched that d to the 5 yet, so we'll just bring it on over. But all these things up top are multiplying, so now our d to the 12 is multiplying by that d to the 5. If we multiply with the same base, we add the exponents. We're not doing anything with the e's, so that can just slide over. And now we have d to the 12 plus 5, which is d to the 17. And that's our final answer. And there you have it, our 4 examples broken down. Hopefully that wasn't too confusing. Practice these skills, and I promise you, it's all going to feel easy peasy over time.